Okay, welcome to the last part of the tutorial. What we did in the part 2 was implementing the solver for this reaction, the Gray-Scott reaction. And this is actually quite good that we did it this way, because right now if your computer is not powerful enough, you can, and this will be in the bonus video, you can externalize this calculation. Right now, you saw at the end of the video, when I was calculating the values and printing the values, the computer was going crazy, especially Grasshopper was going kind of crazy because it was getting like too much data to print, and it almost crashed. But if your computer is not powerful enough, you can start something that is called Colab. That is a Python. If we go to Colab, is this Jupyter Notebook that basically is like an online or cloud platform where you can do some code. So you can do, I don't know, like I in range 100, and then say like print I, and you can execute code. Basically you can type your code and this will print. Of course, because it's Python 3, if you remember one of the tutorials that I made, it says that it was invalid code because this is Python 3, but you can also, I will show you that you can select or configure many of the things. So what I'm saying here is that because this is an online thing, and it will be easier, for example, to pre-calculate some of the values for this reaction, especially because sometimes to get better results, you need, as the ones that I'm showing here, you need 10,000 steps, and that will take minutes in Grasshopper, like I don't know, like 5 minutes. It depends on your computer. If you have a Threadripper 3950 X with 64 cores and 128 threads, probably it will be like easier. Or if there is a way in Python, right now there isn't, there is a way in C# to do it, to use your GPU to calculate this. You can do it in seconds, but this is not the case, so I will show you how to do it with Google Colab, because it's actually pretty nice. You can save your files, your calculation files, to your Google Drive, and then you can use them in Grasshopper. But being that said, let's implement the last part. And the last part, to actually visualize this in 3D, we are going to use this matrix to create curves. And these curves basically will give us the profile to do a loft. Because my implementation, the way that I'm doing it here, I'm using surfaces to create the 3D part. There are ways to do this in meshes that requires additional code, but we will cover that in the C# version of this tutorial. So let's start. Let's start here. Let's create a list, empty list, that will hold our curves. This will be our output, actually. So we will create this definition, this function that we will call create curves. This create curves will take a surface as a parameter. It will take also like which component. We will just call this which. It will basically, we will add a factor for the height of the pattern, and we will use the U divisions and the V divisions, because we're working on a matrix, and we want to basically work also in a surface as a matrix with rows and columns. So we will do we will declare this matrix, and we will say that if which equals A, this matrix will take mat will be equal to A0, basically the calculations for the first component. And if which B mat B0. So basically remember that we have this part here. We can calculate, we can ask this script inside this grasshopper definition to show B calculation or A calculations or concentrations. Then we create an empty array or list. We will create one for the points because we will work with points. Are an array for the normals, an array for t, the tangents. Now we will of course add an if statement that if surface equals none, basically we're not giving this script, this node any surface, return, just don't do anything. And now we will redeem the lists. Redeem. This is like very Visual Basic, old school Rhino script where you had to redimension all your lists or arrays for I and range. I'm talking about like 15 years ago Rhino script when I was in undergrad using for my first master thesis. Not very fun because then Grasshopper came and everything was easier. And I spent nights just coding, but that's okay. So we will redimension all the three lists. So we will do like r point that append 0 times b division or u divisions. It's the same, and we will do the same for the other three. Control C, Control V, Control V. This one was Rn, and this is RT. So yeah, with that we are okay. Next thing we need to also say, actually we can say this here. Now that we are with the if statements, if u divisions equals none or b divisions equals none, if any of those is like we're not giving any value, also return. So we don't get any code error, right? Basically it will say like just stop here. And now we will do something that is like really how can I say, like by default, if you want to work with points on a surface, we will do a loop to get basically to work with the domain of the surface. So basically we will say like eudiv the domain of the surface. We will use the surface domain. We will use the Rhino script syntax to get the domain of the surface. Basically, in a surface that has 4 sides, for example, you want to get the dimension, the domain in one direction, in the u direction, and the v direction. Those are local domains, right? Or local directions of the object. So For that, we will do surface surface, and we will get the first, basically the first parameter that you need to input is the surface, and then the direction. 0, here it says in the documentation, that is for u direction, and we will do the same thing here for the v direction. So we'll say that the v domain is for this. So here we will add a hashtag, like a comment, domain in u, in v direction. Perfect. Now we need to basically plot or get coordinates for each of the points that we are going to use in this surface. So to do that, from the domains, and add a point. To do that, first, because we want to save memory and we don't want to wait for Rhino to draw everything, it's like this, also like this, we will do enable redraw, enable redraw false. Basically this will stop showing stuff on the screen while this is being executed, and then we will enable it again. So we'll say like for I in range 0 to u div 1. So basically we're saying that iterate through values from 0 until the length of the divisions that we're doing, the resolution that we're giving. In this case we have 50 here, the resolution, and steps of 1. And for j in range, another loop, we'll do the same, 0.v division 1, and here we will calculate the parameter. I don't know what is wrong with my keyboard. The parameter u. Basically when you evaluate the surface, probably you know this, or you evaluate the curve, you're getting a local u and v value, right? We're calculating that for each of the value in this matrix to add a point or a surface normal. So we will say that u domain, basically the initial, the lower number of that domain, lower limit, plus I times, how was this, u domain, this is 1 minus u domain 0. Is this the way? Let me check my notes. Yes, this is the way. Divided by the divisions, u divisions, and we will do the same for the parameter v. So parameter v, this will be v domain. This will be, of course, j, because we're going in the other direction. This is v, this is v, this is v. So basically this is calculating like steps to create a matrix of values, evaluating in each point. Imagine that you have the surface and you want to plot this matrix in a surface. Not it can be like any surface that with 4 sides. So this is the calculation. You're getting the upper bound and the lower bound of that domain, and basically you're calculating the steps necessary to do that. And now we want to say that our point, our list, I, j. This is also like really important, like the format. This is why we're working with this 2-dimensional list or like matrices. So in order to keep our data consistent, we calculated our values from the reaction in the same way. So now we can basically work with the same structure, data structure, to actually work with these points now. So we'll do like rs.evaluate surface. evaluate surface. So now we can do the same thing that the evaluate curve or evaluate surface in Rhino does with the values that we calculated here, all these intervals. So we'll say like surface, comma, parameter u. Basically, this is what it's asking you. Evaluate surface asks you for the surface ID. In this case, it's the surface, the u value and the v value. Param u, param v are point. This is I. This is j, and this. This is the normal. We will calculate the normals here. RS that surface surface normal. Look for here, surface normal, and surface normal asks you for the same thing in a slight different format. It will ask you for the param u, param v, like this. So because also if we have a surface, basically we want also the normal of that surface to know how to set the height of the points that we're using. Actually we don't need the RT, so we can, yeah, actually we can just like forget about this. This was another thing that I was trying to calculate probably. I don't remember, this is really old code. So now that we have that, we evaluated the surface, we can create the curves. For that, we need another loop for I in range, height, for j in range, width. Here we need to actually create a list of the curves. Curve. We need to create an empty list that will create a row. Basically, it will take one row at a time, and it will, with those points, will create one single curve. Right. So this is why here in this part, each time you increase one I number, you will create one curve. Then if you go to the next row, another curve, next row, another curve, and so on and so forth. So we do that, and we will say that the vector normal, just like a parameter, equals to rs dot vector scale, and we'll say that the rn I j again, I'm sorry for my typos. It's just like the trackpad of the Mac on Windows is a nightmare. I mean, this is a really nice trackpad, but it has some implementation problems. So here is when we use the values that we calculated. So basically what we are doing, we're just scaling a vector according to the values that we got from our reaction. So here we're saying that each normal you will scale according to those values. So we will say that according to the values from the matrix that we set here, matrix, according to the values of A or B, we need to add a way to normalize these values. So we will say like divided by the C value, and maybe we will add 0.1. Let's see if this works. Then we can add another parameter here to normalize this, and we will say that what did I do here? This goes here, and we can say vector normal is equal to vector add. Basically, we will add this vec normal. We will add this vector to the normal r point I j. So basically we are calculating the new vector and we're adding it. And right now we can say curve that append, remember the curve, this list, we will add this value, vec normal. And here we will do a really nice operation actually. This is why sometimes I really love coding, because right now after we calculate these values, basically we can say that curves that append, remember that we set an empty list here that is called curves. This list will contain all our curves. Curves that append, and here we will do the rs that coerce curve. And rs that add curve. This is the way you create a curve in by script. So curve, and we're missing one parenthesis. So let's see one thing first. rs that coerce curve. It says that help. So basically, this helps you to force that to get the curve that you're creating. That is the one that we are creating here. That the add curve is the same as the grasshopper node definition. You just need to input to create an interpolated curve or just a control curve. In this case, there's another method that is called add interpolated curve, and you just need to give the points that we just created, or the vectors. In this case, we are giving this list of vectors, and once we have that, we might finish this just saying I had an indentation issue there. That this function, this definition here, create curves, will return curves. This will return the curves. So let's see how can we finish this. We have from before at the main call, and we will try to execute this so we don't have any problem. We will call here, how did we call this? Control C, Control V, create curves. We said that for our parameters that we need the surface. So surface here, surface. Then we need which component. So we can say that this is we call this concentration, cons. Terrible number actually. I should concentration, not with uppercase. The C factor, if we're using it, and width and height, that these are called here, so we are fine with that. Yeah, we don't need this. And hopefully this will give us something. So let's test. Of course we have typo. We don't have, there's an unexpected token. Return, oh yes, of course, here. Unexpected token, like 134. Did I close the parentheses here? Yeah, there is something that I didn't close, of course, here. What else? Oh, good. We are fine. So we're not getting any errors. We are not getting anything also here. So because we don't have any surface, so that is actually quite good. We don't want this. We don't want this. We don't want B because we don't have anything and to output, and actually this should be curves. And in our script we should change this last part to actually this will just create the curves, so that's fine. A equal curves. No, actually we should say A equal to create curves. Yes, so now we're done with our code. Remember to save, and let's create just a surface. Planar surface. You might want to reparameterize the surface, so basically that will reparameterize the domain in terms of 0 and 1, like normalize this domain in 0 and 1 in both directions. So set one surface, we'll do this, and this is giving me an error. Let's see. If I try to test this, there is no attribute vector. Yeah, of course. Vector add. All right, voila. You see, we have here the curves. And someone might say like, oh, this is really bad. This looks terrible, Diego. What are you doing? And let's change this a little bit. Let's increase the number of decimals, and we will say that this is 0.01. The higher the number, the more you normalize this, so we can say that this is 0.9. Too little. 0.75. 0.5 maybe. Yeah, that looks a little bit better. So let's hide this. Let's hide this surface also. So we have the planar curves. These are planar curves because if you look in this direction or from the top, these are just profiles that now we can use to loft and create a nice surface. So you see, I mean, it's hard to tell from the curves. Let me go to top view. It's hard to tell by the curves the texture that you're getting. And someone might say like, man, this looks like Perlin noise or just like regular noise. I mean, I could have I don't know, like I could have played with I don't know, like just like random values. But let's to finish this tutorial, because it's half an hour already. If you go to view, no, sorry, display, and where is the profiler widget? Here, profiler. Right now this is taking like 318 milliseconds. Basically this is nothing. Our resolution is not too big. So I'm just going to lock the solver for now, and I'm going to increase the resolution to 100. And I will increase also. Right now we're working with A values. Let's just keep A. And the steps, I will increase this to 500. I always do this because if I increase something, it will lock my computer. You know how nasty Grasshopper is sometimes. So I will unlock this. And right now, my mouse is just like calculating. It's going crazy. The fans of your laptops or your desktop are going crazy because they are calculating not just 20 iterations, but 500, and in a grid by 100 by 100. So that is a lot of calculation that if your computer is slow, you don't want to have it. So look at this. This looks pretty bad actually. This is just one stage of that calculation. So let's say if we change to V concentration. Now it took 26 seconds. You see what I mean when we're dealing with like heavy computation here. So I invite you to actually play with the values. If you go to Wikipedia, for example, or you can find like many concentrations because there are predefined patterns. Look at this is beautiful actually. Look at this. This is pretty nervous system type of quality. If I oh my god, this is so good. I'm sorry, but this is unexpected, so I will save this. This looks beautiful. Preview off. I will do custom preview. Preview, custom preview. The geometry. Look at that. So amazing. Huh? Only 26 seconds of processing time. I will create a material, and with this we will finish our tutorial. The diffuse, I will use a color picker. I want this, I don't know, red. This is actually pretty nice. Maybe this, yeah, this value was too high. So what is the deal here is that if you apply this to any surface, not a poly surface, a surface, you will get patterns. If you play with these values, the concentrations of these values, you will find like surprises. If you go also, while this calculates, if you go to gray Scott reaction values, you can find like some tutorials, of course, for processing or things like that. This website actually I will leave because this is exactly what we just did in code. You can create things like this, which are like amazing, and actually it has like further information about stuff. In this website you can find like predefined values, so you can create like cheetah or I don't know, like worm textures or like zebra fish or things like that. You can play with those values and you will be like greatly surprised. But I'm quite happy with the results that we're getting here. If you want something, I mean, this is a surface, so you can mill this. You can do a lot of stuff. You can remesh this. And actually, I thought it was going to be like a lot slower. Apparently, this is faster in processing than my desktop computer. I will post, like, of course, like the images that I will post at the end of this are a result of applying this algorithm. So yeah, that's it. I mean, as you can see in 3 parts, we made something that is actually quite advanced in terms of coding, which was not a big deal, to be honest. Just like a couple of help functions, the calculation of the solver, and then just like grabbing a surface, plotting points, calculating the normals, and adding these values to a normal to actually get curves, simple curves, to create something like this. You can, of course, always like mesh this, mesh the VREP, and so you can bake this. Look how nice this mesh is constructed. And then you can, of course, like remesh it. I'm pretty happy with the results of what we did here. So that's it. Thank you very much again for watching this tutorial. Please subscribe and share. Always, like, if you learn something here, learn something and teach something. And because that's the idea. That's the idea of making this quarantine tutorial series. I will keep posting more. Next one will be C#, doing hopefully the same, but more advanced and faster. Because we also, like, right now is look at the times that this is produced. Like 26 seconds. It's pretty fast with what we produce, but it's still unacceptable. I mean, I like things faster. Our computers can do better than this, so I will do a C# inspired code from people from, I think, the Bartlett. I will reproduce that code and explain it to you, and we will add parallel threads to make this faster, and also to have the freedom to work with meshes. So yeah, stay tuned. Please subscribe and follow and share. Thank you very much.